So say we are given a subset A of a space X. So A is included in X, and there are maps between spaces X and Y. There are two maps, F and G. And both these maps are equal to each other on the subset A. That is, they agree with each other. So we want to define F is homotopic to G relative to this subset A of X. Now the definition of F homotopic to G relative to A is, first, there should exist a homotopy. So there is a homotopy between F and G. So there is a homotopy between F and G. And in particular on set A of X, so on the subset A of X, we already know F is equal to G, but the homotopy is also equal to F and therefore equal to G. So on this set A, homotopy H A comma T, this is the same homotopy which is between F and G. This is equal to F of A, which is equal to G of A on the subset A. So for all T element of 0, 1. So you have a homotopy, but you can see this homotopy makes sense only outside A. On the set A, everything is equal. So standard example is, say you have 2 points 0, 1. They are the boundary of the unit interval 0, 1. And the 0, 1 say goes into some space X. So we are now talking about path homotopies. So F is equal to G on this 0, 1 set. So you have, say, path F in red, and then in rust color you have path G. So we say path F and G are homotopic to each other, and at their boundary F of 0 is equal to G of 0. So they agree on the set A. The set A here is the boundary of the unit interval, and F of 1 is equal to G of 1. So you write this as F is homotopic to G relative to 0, 1. So these are nothing but two homotopic paths which have the same endpoints. So F is homotopic to G relative to the boundary of the unit interval 0, 0, 1. Now we want to talk about a category. So this is the homotopy category. We will denote it by H top. So first, what are the objects of the category? So objects of the category are nothing but continuous maps. So say you have two spaces X and Y, and you take the continuous map. So F is the object of the category. Now we want to define the morphism. So morphism is the homotopies between these maps. So morphism from, say, map F to map G is nothing but a homotopy. So now I'm using the interval 0, A rather than 0, 1. So H of X, 0 is F of X, and H of X, A is G of X. So after this we want to define composition. So suppose we are given another homotopy, say H bar. So this homotopy H bar is homotopy, say, between map G and H. So X times 0B and goes to Y such that H bar of X, 0, this is G of X, and H bar of X, B is small h of x. So basically I'm saying is G is homotopic to H via this homotopy. So then we can construct a new homotopy G, which is x times 0 to a plus b and goes to space y. So we split this into two parts. When t is between 0 and a, we take the homotopy H. And when t is between a and a plus b, you write g of x comma t is h bar of x comma t minus a. So now you can plug in both 0 and a plus b and check. We go from f to h. So we have been able to compose two homotopies to get another homotopy. So now we want to talk about home functors. So home functors in this homotopy category, which we will denote by h top. So say you're given the object f, which is the map from x to y. So then say you are given another map, say map from z to x. So this is map G, and you already have map f. So then you can form a map from G to y by first applying G and then f. So we will call this operation as f subscript a star. So that is nothing but f star takes these homotopy equivalent maps from z to x to the map z to y. So obviously you're given map f, so you're given a map G, you first apply G and then you apply f. So second operation is, so again you're given map f from x to y, and then you're also given a map from y to z, say map h. So from here you can get a map from x to z, which is first apply f and then you apply h. So this is equal to map f superscript star. So f superscript star takes the map from y to z to a map from x to z. So h gets mapped to first apply f and then you apply h. So now we talk about this homotopy equivalence. So we are just going to repeat the definition which we have already covered. So a map f is an H equivalence or an isomorphism. Yeah, so if there exists another map G such that, so you have map f going from x to y, then you have a map G going in the opposite direction. First you apply G and then you apply f, you will get ID on y. So this map is homotopic to ID on y, and GF is homotopic to ID on x.